All right, y'all. So I'm going to go through some principles, hopefully, that will help you with the elevator lab. Now, this is not going to answer all the questions, but hopefully it'll touch on a couple of things that will be helpful to you. All right. So here's my data. I just went and did exactly what you guys did. I wrote in the elevator. I got my initial reading at rest and wrote down all the data for each of those different positions. Now, here's the first thing that I want you to recognize. Recognize that my initial reading when I was at rest was 95 kg. All right. Now, when I was at rest on the bottom floor, I got 94 kg. Right? Now, those two should not be different, right? Those two should be the same because I'm at rest in both situations. Now, the fact that those two are different means that my scale is off just a little bit, right? It's not super consistent. It's not always precise to the same degree. And so therefore, what we want to do is we want to say, well, if those two should be the same, then really anything that's about 1 kilogram away from this is approximately the same, right? And so this one right here, this is also 94. That's the same as this one. That should be approximately the same as those. The same thing with this one, right? This is 96. That's only one more than the 95. This is approximately the same as each of those, right? The other numbers, those are all quite significantly different from that initial 95. But the fact that these two right here should be exactly the same and yet they're off by 1 means that really anything that's off by 1 from this 95 is approximately the same. All of these should be about the same. All right. Now, the next thing I want to do is talk about this. Now, this 95 is my mass, right? Now, this is not what you're going to write in these spaces here. You're going to put what you think. You're going to put some other things here. But my mass is 95 kg. And I know that because my scale is going to tell me what my mass is when I'm at rest, right? Now, the rest of the time, the scale is actually going to measure how hard I'm pushing against the scale. It's going to measure the normal force of the scale on me, or the normal force of me on the scale, right? But I do know that my mass is 95. Now I can get the force of gravity from that. So the force of gravity is mg, if you'll remember. So 95 times 9.8. And so if I do that, I can go 95 times 9.8, and I get 931. So the force of gravity is 931 newtons, right? 931 newtons is the force of gravity on me. Now that is always the force of gravity, right? It doesn't matter if the elevator's moving down, if the elevator's speeding up, slowing down, if the elevator's moving up. The force of gravity on me is always 931. Done, right? No questions asked, all right? Now the scale is reading the normal force. But of course, the scale doesn't actually give us normal force. The scale gives us this number in kilograms, right? But we know that when I'm at rest, if I were to draw my free body diagram, that I would have the force of gravity down and the normal force, which is up, and that when I'm at rest, those two should be equal because I'm maintaining my state of motion. So if those two forces are equal, then I know that my normal force is also 931 newtons, even though it's reading 95 kilograms. Now, what I can learn from this is that my normal force in any situation is going to be this because the scale is measuring the normal force. But then just like I multiply my mass times g to get the force of gravity, I can take that number and I'm going to multiply it by 9.8. And that will give me the normal force of the scale at that point in time. Now, if you think about this, let's go ahead, let's try that out. 87 times 9.8, that gives me the normal force, which is 852.6 newtons. If I look at the free body diagram, when the elevator starts to move downwards, my force of gravity is still that 931. But the normal force has to be less so that I can accelerate downwards, right? This is Newton's second law. Because the force down is bigger than the force up, I accelerate downwards. You'll notice that I calculated a normal force there of 852.6 newtons. All right. So what I'm measuring on the scale is trying to tell me how hard I'm pushing on the scale, the normal force of me on the scale or the normal force of the scale on me. That's what it's trying to tell me. But the scale has been made to give you kilograms instead of newtons. So the way to get from kilograms to newtons on a bathroom scale is to multiply by 9.8. So each of these should then give me the normal force at that point. We'll see exactly the same thing in each of these situations. All right. So that's going to be important as you do the calculations later on. Okay. Number one, the force of gravity is always 931. And number two, you can get the normal force by taking the kilograms that the scale is reading and multiplying it by 9.8. All right. So I'm going to go through a couple of these with you just so that you can have an idea of what's going on. All right, I'm not going to do the elevator at rest because that's a little bit easier one. Let's jump down to this one. Let's try the elevator slows down to a stop. All right, so here we go. Here's our object. We've got the force of gravity pulling down. We've got the normal force of the scale pushing up. Now, think about this. It's moving down and it's slowing down. All right. If it was moving down and gravity was bigger than the normal force, then the acceleration would be downwards. If it's moving down and accelerating down, it's going to speed up. So what I need is it's moving down, my velocity is downwards. In order for it to slow down, I need my acceleration to be in the opposite direction. I need the acceleration to be upwards, which is why the normal force needs to be greater than the force of gravity. Now, below, we're going to write an equation for Newton's second law, which remember, Newton's second law is sum of the forces equals ma. So the sum of the forces here is the normal force, which is upwards, minus the force of gravity, because the force of gravity is downwards, and that will equal the mass times the acceleration. Now, it doesn't ask you to do this until number 6. It says, knowing my mass, calculate the acceleration of the elevator in each situation. So now in part 6, it's actually going to ask you to calculate it. I'm going to go ahead and do it here just so that we keep everything together as I'm explaining this in the video. So remember the force of gravity. We calculated the force of gravity before. The force of gravity was 931 newtons. So I'm going to go minus 931. Okay, my mass is 95. That doesn't change either, right? No matter what the scale says, my mass is 95. That doesn't change. So the mass is 95. I don't know the acceleration. The normal force I can calculate, right? Remember, the normal force I can calculate by taking what the scale is reading and multiplying by 9.8. So when the elevator was slowing down to a stop, and a lot of you mentioned that you felt heavier, right? When it was going down and it was slowing down, you felt like you were heavier. You're pushing against the scale with more force. And that's what we read. So if I take that 102 and I multiply by 9.8 because the scale is giving me kilograms instead of newtons, then I can go 102 times 9.8 and I get 999.6. So that is going to be my normal force. So 999.6. There we go. And so now I should have everything that I need in order to calculate the acceleration, right? So I got 999.6 minus 931, and I get 68.6 equals 95a. And then I can divide both sides by 95. And I get 0.722 equals A. And that, of course, is meters per second squared. Notice that I get a positive number, just like I expect, right? I expected my acceleration to be upwards. it should be a positive number. That also is because the normal force is larger than the gravitational force, just like we saw here. The normal force is greater than the gravitational force. Everything connects. Everything should make sense. Everything should then connect with everything else, right? All right, I'll go ahead and do one more just so that you can see what it might look like in a different situation. I'm not going to work through all of them. Okay, what I do want to do is recognize, this right here, the elevator moves down at constant speed. Well, recognize that here we said that this 94 is essentially the same as that, right? The only reason I'm getting different numbers is probably because of my scale, right? 94 when I'm at rest should be the same as the 95. So these should essentially be equal, right? So if I draw the free body diagram, I should have the force of gravity down and the normal force up, normal force of the scale up. If it's constant speed, these two should be equal. Now, in this situation, I didn't actually get them to be equal because of the scale. So how you want to approach this is up to you. If you want to say, you know what, those two are equal, it's constant speed, therefore the acceleration should be 0, Fn minus Fg equals ma. And so you could say the normal force, you could just say that those two are the same, acceleration is 0, and you can be done with it, right? If you want, you could say, yeah, but that's not what I got, Mr. Bauer. I got 94. All right, well, let's go ahead and see what it would look like if we did 94. All right, we know the force of gravity is 931, so I'll put 931 there. We know our mass was 95, okay? And the normal force, remember, is going to be the 94 times 9.8. So 94 times 9.8, all right, which we get 921.2. And now we should be able to solve. We'll do the 921.2 minus 931. And we get negative 9.8 equals 95a. Divide both sides by 95. And we get negative 0.10 meters per second squared is equal to the acceleration. So notice that we get an acceleration that is so small, 0.1 meters per second squared, that it's basically nothing compared to the acceleration that we found before. All right, so I'll leave it up to you how you want to calculate that. If you want, you're welcome to recognize that because it says constant speed, I should be getting 0. That corresponds with what we have here. We recognize that the 94, the 95, those are essentially the same thing. All right. Let's do one where we get a negative acceleration. So I'm gonna skip up here. The elevator is moving up and slows to a stop. All right. So let's look at this one right here. And this will be the last one, and I'll wrap up the video. I think most of the rest of them you can figure out from the things that we've been talking about here. So of course we still have that force of gravity down, which we know is still that 931 newtons. And then we have the normal force up. Now, should the normal force be greater than, equal to, or less than the force of gravity? Well, it's moving up, right? And it's going to slow down so that it stops. If my upward force was bigger than my downward force, what's going to happen? Well, if the upward force is greater, it's going to have an upward acceleration. And if the upward acceleration is with the upward velocity, then it should speed up, right? Anytime your acceleration is in the same direction as your velocity, it should speed up. The fact that it's moving up and slowing down must mean that the acceleration is in the opposite direction. The acceleration must be down. It's moving up, but it's slowing down. Kind of like when you throw a ball up in the air, right? When you throw a ball up in the air, the acceleration because of gravity is negative 9.8. It's down. And yet the object's moving up and it slows down, comes to rest, and then it starts coming back down again, right? So this is very, very similar to that, is that we're gonna need a down acceleration in order to slow down that upward velocity. And so I'm gonna actually say, you know what, I need my force of gravity to be larger, and then my normal force is gonna be smaller. Now the normal force, if I look for the elevator slowing to a stop, that would be this guy right here. I got 90, which if I do times 9.8, I don't know, 90 times 9.8 is 882. So that's 882 newtons. All right. Now here it would be the normal force. So I've got the normal force, which is upwards, minus the force of gravity. This is just sum of the force equals ma, just like we did in the mini lab, right? The normal force was 882. The force of gravity is 931. The mass is still 95, just like it was from the very beginning, right? Times A. So I'm going to do 882 minus 931, which I get negative 49. So I have negative 49 equals 95A, and then I'll divide by that 95, and I get that the acceleration equals negative 0.52 meters per second squared. And notice that I do get a negative number to match the downward acceleration, just like I said there should be. So once again, everything should connect. Everything should match. The downward acceleration means that my upward velocity is going to decrease. I have a larger force downwards than upwards, just like I expect. The difference in those forces is what is going to cause that negative acceleration to occur. All right? So hopefully that is helpful. You can use that same principle on all of these different situations in making sure that you kind of understand each of them. If you have any questions, please, please, please come ask me. All right? I'm glad to help you out. I'm glad to help make sure that you understand what's happening in these types of problems. But this really is all about just recognizing how to pay attention to the balance of the forces, the acceleration using Newton's second law, right? And so I hope that that is helpful. And again, let me know if you have any questions. All right?